Hi everyone, I'm Rahul and I'm going to tell you about our work on adversarial robustness in discontinuous spaces via alternating sampling and descent. It is well known that deep learning models are vulnerable to adversarial examples crafted by adding visually imperceptible noise to an image. To defend against these attacks, gradient-based adversarial training works well as the loss landscape is more or less smooth. However, the practical applicability of these defense mechanisms is quite limited as pixel perturbations seldom occur in the real world. Some past work has explored more naturalistic perturbations such as 2D and 3D scene transformations. For these settings, it has been found that gradient-based adversarial training is a less reliable defense due to the discontinuities in the loss landscape. To handle such discontinuities that occur in real-world perturbation sets, we introduce a novel optimization framework. We also collect a simple dataset of traffic sign models to serve as a benchmark for evaluating robustness with respect to 3D scene parameter changes, such as camera movement and light modifications. Our optimization framework switches between global zeroth order sampling and local gradient updates. Concretely, the framework consists of a sequence of three steps performed iteratively. It starts with sampling a probability density defined in the perturbation space, followed by first order sample updates, and modification of the density function's parameters using updated samples. Under this framework, we design a powerful optimization algorithm for robust model training called alternating evolutionary sampling and descent, or ASD. Our algorithm combines projected gradient descent with an evolutionary optimization method based on covariance matrix adaptation, which is a widely used method for working with difficult optimization landscapes. To procure robust models, we perform adversarial training using this optimization framework. We use the robust test accuracy metric for evaluation, which measures the accuracy on test set adversarial samples generated using a given attack method, such as PGD with random starts, a proposed attack method, ASD, and a version of uniform grid search where the grid samples are updated with gradient descent. We find that our proposed adversarial training method achieves state-of-the-art robustness against 3D scene parameter perturbation attacks evaluated on our traffic science dataset. ASD also outperforms prior methods on robustness to patch attacks on the CIFAR-10 dataset, where both the discrete patch location and patch content are jointly optimized. In this work, we developed an effective method for defending against physically realizable adversarial attacks. An experimental evaluation on our new traffic science benchmark suggests superiority of the proposed adversarial training method. We hope that our new benchmark dataset will help advance research in this area. In future work, extending the benchmark beyond simple traffic signs to a more general setting with arbitrary 3D models will help in better assessing defense mechanisms. Another interesting research direction is to find defenses in this setting that do not rely on computationally expensive adversarial training. Thank you. Please refer to our project page for more.